All right, yeah, welcome back. So we want to quickly look at how to test for normal distribution, especially for our parametric test, and also looking at outliers in our data, how to manage outliers in our data. Don't forget that normal distribution is one of the assumptions of parametric test. We're going to look at that in under statistical analysis. But before that, you must understand what normal distribution is all about. We also have, apart from that, we have what is called homogeneous of variance. We're going to look at that here also. And also, we also have test of independence. We also have independence and outliers. So independence is not a challenge, actually. That one is always taken care of most times. But the outliers, normality, and the homogeneous of variance, there are three most important assumptions in the parametric test. So we want to look at them under this particular heading. Actually, outliers is the random component of measurement error. Any data point that is significantly outside a distribution's means or median is an outlier. Outlier is nearly always present in data and can sometimes be difficult to get rid of. Okay, outliers are something we should remove from the data set so that it doesn't skew the model. This outlier, like I said before, if you remember in my previous slide, that they are mostly caused by intentional dummy outlier created to be tested detection method. During the dummy outlier created to test detection methods. Okay, we also have maybe data processing errors. We have sampling errors. We have or data entry errors. These are human errors. So this could be it can cause data processing. So data outliers. This process of minimizing outliers is called smoothing. All right. So before we go to outliers, let us first look at normal distribution. I'm going to be using I will be creating a sample data first. Let's remove this. Let's just start by creating a sample data of our own. Let me run the two library we have here, tidyverse and base test.r. The purpose of tidyverse is to perform a data analysis on our data. So we also and to get some data set. Also, this one is to be test.r is to get to do normal distribution, right? So we can run this line. So this line, you get a data set called data. So we call the function normal distribution from this particular base tester, right? This is to get a. You can also use a q norm for this, okay, or r norm for this, all right? So depend on which one you prefer. All right. So if you run this line, for example, I've already have a data now created already. So let me keep this. Let me comment the empty cars, which is in between, we're going to use later. But at least let us start with a normal distribution to see how data is normally distributed first. All right, so this is our new data set now. We have only one variable or column there called n, so which have a mean of 0 and SD and the definition of 1, and we have 100 observations. All right, so we want to create a histogram first to see the output result of this data, how it look like. So if you draw this histogram, you can see here, you see histogram, how it look like. So this is a normal distribution. Okay, this histogram is normally distributed. All right, and you can see the variance here is homogeneous. All right, so you can plot the density plot of this also. You can see density plot of it. You can see it's supposed to be bell shape. So this must be bell shape. So this is a sample of graphical sample of normal distribution data. All right, but let's create more of this data. Let's create a histogram together with a combine together histogram together with this. Let's see we create like this. So let's say we have both histogram together with this. All right. So this is a histogram and let's combine together. So we see how our normal, this is how normal division data should look like. All right. So this is the mean for in between mean here. So when it's normally distributed, the mean equals to median. Okay, they fall they fall upon themselves. So if the mean is 0, the median should be 0. If the data if it's normally distributed, all right. All right, so let's go further and see what I'm talking about. We can see use a Q norm to test also to see. I've shown you like that in the past. If you remember, and I was talking about this. As you can see, when it is skew to the right here, the left. So this this left here, right? Don't forget this particular slide I showed the other time, right? Then media is greater than me, right? That's mean there's a sense of outliers in the system, right? When it is a skew to the positive skew to the right, it means that the right tail, it means mean is greater than median, all right? But when it is symmetrical, 50-50%, that's mean equals to median equal to mode equal to 0, which means no outliers, all right? So that is when you are dealing with but we also use kurtosis to sort of check, okay, to check the outliers possibilities in the data. All right, so this is how we explained last time, and that is not how. We also use a box plot to explain. Okay, I use a box plot to explain it can be skewed left or right or symmetry as well. So you can see these are called outliers. Okay, these outliers box plot, right? And I give a sample, but not only that, you also use a QQ plot, all right, to select this normal QQ plot to explain the presence of outliers at the same time the normality of a data. So this one is at least very close to normal distribution, close, but this one is not. You can see it's outside the straight line. All right, so this is how to check. All right, so if you come back to our data now, for example, you can see this now. Okay, this is normally distributed. All right, so it's not a. Let's now use a other data set to check now. Let's look at our box plot first. Box plot. So there's no outlier here. You can see the mean is in between here. So this means this data is normally distributed. That's what it means. All right. Okay, so we can test this data further. Okay, we can test further by let me check. Let's say we have data. Let's say data. Let's say our histogram is data. Okay. Our let's say we got data. We have the mean. We have to find the mean of data. We want to see if it is skewed left or right. Right. Data. So if you run this now, you're able to see this outline mean data. We want to mean red and median blue. So if you run this as histogram now, should be able to give us a structure of our data. All right. So you can see the blue is on top of the red. Okay. So which means they are equal. So there's a red under the blue here. There's a red under the blue. You can see that. So but both of them, they fall on the same line, which means is a they are. So we can see use other data to confirm what I'm talking about. So let's use what they call it now. Let's use inbuilt data called empty cars. All right. So let me use it empty cars. Empty cars. Let me first attach empty cars. Last time I removed it. So let me attach it again. Empty cars. All right. So you can check empty cars with our former this thing here. So let's assume that we want to check for empty cars here, for example. We can check the variables we have. Let's first describe empty car. Let's describe what is inside the empty cars first. Let's say we glimpse it. Let's glimpse empty car, right? Empty cars. Let's see what is inside. Okay. So under empty cars we have okay. That's what we have. We have mpg, miles per gallon, cylinder, displacement, horsepower, and so on. So we have this is what we have under empty cars. Right, these are our variables. They are all numeric variables actually. Okay, so it makes the work even easier. So we can run and see the skewness of these variables in empty cars. You can see the skew. Let's say we want to use a horsepower and a weight and displacement, for example. So let's run this line. This horsepower, for example, for positive skew. Run this line. Okay. Okay. Now, okay, it's showing me empty cars like HP. Don't forget that if you want to access any variable from the dataset, you have to use $sign. All right, we have done that before. So now look at it now. This is a skew. Look at this. You can see it here. So this our the blue is our median. The red is our mean. So which means the red is more than the blue, which means the mean is greater than the median. They're supposed to be equal, right? Which means this data is skewed, right? It's not a normally distributed. So, right? So you can do the same thing for WT, for example. Run WT also from our empty car data set. We also see that this one is also skewed. All right, you can see this red mean, this median. All right, so now median mean is greater than median now at this point. So this is called negatively skew. That former one is called positively skew. So you can plot. We can also plot. Let's say we first plot for HP. Let's plot for HP first and declare that horsepower first. Let's plot for HP and see the density plot. How it look like. See how it look like. You can see it's skewed, positively skewed. You can see that. All right. Let's see. Okay. Let me first plot for WT first. WT. See that one negatively skewed. You can see skewed here. Okay. If you also plot for the QQ plot for that. See, look at the QQ plot. You can see outliers here. Outliers here. You can see it's not on the straight lines. Even the bus plot. Let's see the bus plot. How it look like. See the bus plot. You can see outlier here. You can see it's not in the middle. All right. So these are the test. So if we also further and check the test for normal distribution by using Shapiro test, so you can so apart from the graphical testing, you can also go further and confirm our test to make sure that to see that this is not let's say we test for WT, for example, using Shapiro test. All right. So if you run this now, normally if significant, it means no normal distribution. All right. That's what it means. Normality failed if significant. That is, if it is less than 0.05, but if higher than 0.05, it means that it is a normally distributed. So let's run this line and see what I'm talking about. You can see this 0.09. All right, this 0.09. This shows that it is higher than 0.05. All right, it shows a sign of normality. All right, even though it's not normal, but in our diagram fails automatically, but which means something can be done to this particular WT to make it to improve it. All right. Okay, so let's go further and see and use HP. Let's use HP. 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 We're trying to see the difference between the two parameters, so that between variables. Let's say we run a density plot for this. You can see we have done that before. So let's see also you can see that outliers here for QQ plot for HP horsepower. So if you run the bus plot as well, you can see some outliers. See outlier only one. All right, which is not too bad. All right, so if you run the Shapiro test for HP, what do we have? That 0.04, which is also 0.04 is also significant. Okay, this is significant. you can take it as significance, okay, which means that it's not normally distributed, okay. That means it fails ability test, right? But the former one 0.09, don't forget that one 0.09. That one seems to pass, okay. That one is greater than 0.05, okay. So, but we see do a further test. Right, so let's do a further test. We have a library called summary tools as well, whereby we can describe our data properly. So if you run this now for HP, describe HP, okay. Let's see what we get under this summary tools. This one gives us the under HP we have a mean, standard deviation, okay. We have a minimum Q1, quartile 1, median, quartile 3, maximum, mean average deviation. We have IQR, the quartile range. We have CV, we have skewness 0.75. We have kurtosis minus 0.1. That means negative skew. That's what it means. So that's why it's negative. So these are the things we have here under the to see more about our data. So we can go for the test for homogeneous variance for each of them as well by using the you can install a package called car. This package can help us to test homogeneous variance. So if we use what you call living test, all right, our Y will be mtcar.mpg or HP, anyone that we want to test, all right. Then we can have a group. This one is factor group, okay. Your cylinder is a group. It's a group variable there which we supply. So if you run this line now, for example, this is significant now, all right. So this means this one failed. The fails homogeneous test. So let's use for SCHP. HP horsepower. That is a 0.07. That is a so see 0.07 is greater than 0.05. This means this one, I think it pass. All right. Okay, so let's use WT. So this one also pass, right? Homogeneous variance. So this is just to confirm, all right. But we can see that we can still use what they call it now, parametric test for this particular data if we need to, because you can see that he has some assumption passed, all right. So we can still use not all that fails, even though our data can be a little bit maybe improve upon, can improve on the data set a little bit. That's what it means. You can do some improvement. You can remove the outliers. Okay. So let us see how do you manage outliers. All right. How do you manage outliers? We install the package called the look first. The look. So let's run this called the look. So under this package we have what they call diagnose outlier first. Our data set is called empty cars, and we have these variables or these columns. We want to observe. Want to investigate the outliers. All right. If I run this line of code now, I pass my data set here. Right. You can learn more about diagnose outlier here. Okay. Diagnose. Just type diagnose. Okay. Diagnose outlier. So you can see more of that here. It's okay. So look at it of numerical variables. So deal with the numerical variable only. All right. So you can just see the how to use here, what it's meant for. Okay. All right. So look at the details. All right. This is how to use. You can check. You can see more about it here. So now let's just run this line of code and see what I'm talking about. Around this line. Okay. Let me just close this. Let me run again. All right. So we have 3 variables that we are trying to look for variables. MPG, HP, WT, and displacement. This one, no, you can see variables are here, outliers count, all right, outliers ratio, outliers mean. So the first one, MPG, no outliers, okay. HP have 1, WT have 2, displacement have none. So we are able to see how do we remove outliers. Sometimes can be 100, can be 50, can be more, all right. So the same procedure follows, whether it's 1 or 2, doesn't matter. So we have to learn how to remove them. So we can manage them using the same deal look, all right. So let's see how we handle this. All right, so we can do the correction now. We can correct one by one, or we can correct all together at the same time because we have only 2. All right, so by using this method called correct input outlier, so we can pass, if we want to correct only one for only HP, for example, we can use this method, call it input outlier. That's what you do, input outliers. We call this function from the deal look arrow, pass our data set here, and we can pass our HP or WT, whichever one we want to use. Then our method is capping method. We have many methods here because if we go to let's say we have let me just show you this. We have under input input outlier. If you scroll down, you see here this input outlier here. You have how to use it. You can see the function here. This data we have the ever method, not attributes. Ever is the variables you want to pass in. You can remove ever, just put the variable there only. It's allowed, okay? There's no problem. So no attribute can be removed. Okay, you can set it to false or to true, depends. So we have 4 methods here. We have mean, we have median, we have mode, we have capping, right? So capping is very powerful, okay, more powerful than each of them. All right, so they use lower and upper quarters, 25 and 95%, okay. So that is very powerful, 5% and 95% percentile to check the lower and upper bound of each of the variables. So but we are going to be using the if you can try each of them, okay. You can try each of them. I've tried each of them, and I see that capping is better, okay. That's why I use capping here. I've tried mean, mode, median, but capping seems to be an improved version of this. So let's create a new object here called new empty cast now. That's become our new data set now. So we pass our data set inside because we want to do it together. You can use this line of code, call it correct. Okay, so but we don't want to do it one by one, we want to do it together. We can have a whole data set, a new set of data sets now. So we have to use let's call it a new empty cast. So we call the original empty cast here, which is our data set. We pipe in our mutate, which we use mutate, this piping now, we use mutate function, and we create a new variable called inputate HP. So this is our new variable for HP. So we have HP already, don't forget. Okay, this is HP here. Okay, so but we want to create a new variable using mutate function, create a new HP, then we pass our input outliers here, our dataset checkers, we are using HP, okay. Method is capping, no attribute is true. So because it's only 2 that have outliers, okay, don't forget HP and a WT. So we create another variable called input WT. We're passing our function here, input outliers, our empty cast is here, WT is here. All right, so our method is capping and no attribute is true. So we want to run this line, this code now to see if it really works. That means we have, in addition to HP, we have input HP, and in addition to HP and WT, we have additional variables called input HP and input WT, IMP HP, IMP WT. So which means we have more variables. So we can be able to differentiate between the old and the new. That's what it means. So this will be the old, this will be the new. All right, so create a new one. So the new one is now we want to assign our input outlier to now to see the effect of our outlier. So let's run this variable now and see what I'm talking about, this object. So it's run now. So for us to see the result, we have to call this this one. All right, so let's diagnose now again. Now we have run the line. So let's diagnose again and see the result. So we call diagnose our part our new applicants which we just created now. This one. Don't forget this is the one we just created now. All right. Let me put this one down. So we just created this now empty cars, which is we assign all our work here to. So we call it here to diagnose. Our MPG is inside. This new one is inside. This is inside. If our display is inside, we still have something is missing. Okay. All right. All these ones they are inside, including the HP. All right. So let's include HP. We don't need to include HP anymore because we know that the HP have outliers, okay, and WT have outliers, so we don't need to include them. All right. So we just want to confirm. Let's confirm if these ones that we have created now, or we can glimpse. Let's first glimpse this. Let's glimpse this and see what I'm talking about. Let's glimpse. Now we have glimpse. And we have can see this. So we have our HP here. All right, displacement HP. So we have the ability. We have a new variable called input HP and input ability, which we have done. You can see that it has done it already. I see that has done it already. So it has input and layers for us. All right, so good. That's a good job. All right, that's what Capping did for us. So we can now diagnose again and see the difference if we see have outliers. All right, let's run this line of code. Let me just create more space here. You can remove this particular displacement. It's not needed actually. So okay, let's run this. So now we have a outlier count 0, 0, 0. You see, you can see now it has gone HP. I mean, IPNT, IP. So it's no more there anymore. All right. But if you run the HP, we can see have it there. But for new one, let me include HP to understand what I'm saying. If you have HP, let's say we have HP included, right? We have WT included, right? All right, let me remove this. Okay, we don't need this. Okay, to create more room. All right, so if you run this line of code now, you can see the HP we still have. Okay, let's run this. All right. You see, we have a HP still have 1, WT have 2, but our new variable called input HP 0, input WT 0, which means that what we did worked. All right. So we can create a new bus plus now again. Okay. Let's create 2 for bus plus now. Let's create one for HP, one for the old and one for the new. Let me just copy this and paste so that you can see the difference between the old and new. All right. All right. So we have empty cars. HP. All right. So we also have new empty card input HP. This is our new one. Right. So if you run this line of code now, each of them. Right. See, this one will have one outliers here. All right. If you run this line of code now, you can see no outliers. Outlier is gone. That's been taken care of. So let's see the WT as well. WT, and then this also WT. All right. If you run this line of code, we have 2 outliers. You can see 2 outliers here. All right. So let's run this line also. No outliers. They are gone. So which means this particular method can handle outliers properly. Okay. After we diagnose it. So we now have a new data set called a new empty cast now, which you can save. How do you do that? You can actually save that. Just a write .csv. All right. The name is called new empty cast. Okay. Comma file name equals to open quote, call it new underscore empty cast.csv. So it will be saved in your directory, your what do you call it now? Working directory. All right. So when you run this line, it's saved. All right. So you can browse it. All right. You can browse it and check what is there. So that is how you create. So there are other way you can also log. You can log this skewed. If the thing is badly skewed, you can try and log it and see if they're going to improve the outliers or the skewness. You can improve it negatively or positively. Any one of them you can improve. You can try to check all this to log this one, or you can also you can do square root of them, you can inverse. Okay, so these are just things you can do on those variables before you perform your testing in case they are not normally distributed. Okay, but don't there are still other general transformation we have here. This one are good for machine. They are good for machine learning. So don't use this one for your data you want to use to perform statistical analysis. Okay, they are only good for machine learning. If you want to do machine learning, for example, you can standardize the data by scaling it. You can also normalize the data, all right, using maximum and minimum scale data. So you can pass your data here and scale it, right? Or you can perform exponential or a quantile transformation. All right, so this one can be performed on there, but this one, the problem is that if you perform this one, it will change your data shape completely. So it won't be good for statistical testing anymore. That means your data or your originality is lost. That's what it means. So, but for machine learning, they are very, very good. Machine learning, you can just use them for machine learning. All right, but when it comes to statistical analysis, don't use those ones. You can use these ones. Yeah, your square root, or you inverse, or you log it. Okay. Don't go beyond that for statistical analysis. Just for to improve the normality of your data, you can do that. So that is that for today under this particular section, and I think you can apply this easily, and I will see you in the next section. Thanks so much for listening. Goodbye for now.